Oh, welcome to our voyage through the cosmos as we explore an intriguing question. Is there a limit to how large a planet can be? The universe, as we know it, is teeming with a vast array of celestial bodies, each unique in its own right. Among them, planets hold a special place in our quest for understanding the cosmos. From our humble abode, Earth, to the gas giants of our solar system and beyond, to the exoplanets orbiting distant stars, the sizes of these celestial bodies vary significantly. But is there an upper limit to this variation? What factors govern the size of a planet? These are the questions we will delve into, exploring the role of planetary formation, gravity, atmospheric escape, and more. So buckle up as we embark on this exciting journey to discover the boundaries of the universe. Stay tuned as we traverse the cosmos, seeking answers to these celestial mysteries. Before we dive into the size limits, we need to understand what exactly defines a celestial body as a planet. So what is a planet? Let's simplify. According to the International Astronomical Union, a planet is a celestial body that orbits around the sun, is spherical in shape, and has cleared its orbit of other debris. But wait, it's not just about the shape and orbit. Mass and gravitational forces also play a crucial role in planetary formation. You see, planets are born from a swirling disk of gas and dust surrounding a young star, known as a protoplanetary disk. The solid particles within this disk gradually stick together, forming planetesimals. If a planetesimal acquires enough mass, its gravitational pull will attract more and more material, allowing it to grow into a planet. The process doesn't stop there. A true planet not only forms, but also survives. It must have sufficient mass to hold onto its atmosphere and withstand the harsh conditions of space. At the same time, it shouldn't be so massive that it ignites nuclear fusion in its core, or else it would become a star. But there's more. A planet must also clear its neighborhood, meaning it must be the dominant gravitational force in its orbit. It should be able to scatter away or capture smaller bodies in its path, ensuring that it's the only kid on the block. And lastly, a planet needs to orbit a star. This criterion excludes rogue planets, which roam the cosmos without a star to call home. So, to sum up, a planet is a celestial body that orbits a star, has a round shape due to its gravity, cleared its neighborhood, and has a balanced mass. Not too little to lose its atmosphere, not too much to become a star. Now that we've laid the groundwork, let's delve into the heart of the matter, the size limits of planets. Planets come in all shapes and sizes, but they primarily fall into two categories: gas giants and terrestrial planets. Now you might be wondering, what's the difference? Well, the key lies in their composition. Gas giants, as their name suggests, are predominantly made up of gases. Jupiter and Saturn, the behemoths of our solar system, are perfect examples. These giants are primarily composed of hydrogen and helium, much like the sun. Their enormous sizes are a testament to the vast amounts of these light elements they've managed to accrue. On the other hand, we have terrestrial planets. These are rocky bodies, much like our own Earth. Mercury, Venus, Earth, and Mars all fall into this category. Made primarily of heavier elements like iron, nickel, silicon, and oxygen, these planets are significantly smaller than their gaseous counterparts. But why does composition matter when it comes to size? It's all about density. Gases are less dense than solids, meaning a gas giant can hold a larger volume of gas for a given mass than a terrestrial planet can hold of rock. This is why gas giants can grow to such colossal sizes. However, size isn't everything. While gas giants can grow to be large, they lack solid surfaces. You couldn't stand on Jupiter or Saturn. You'd simply sink into their gaseous atmospheres. Terrestrial planets, on the other hand, have solid surfaces. Their smaller sizes also make them more conducive to life as we know it, but that's a topic for another time. So we see that the composition of a planet plays a crucial role in determining its size. Gas giants, with their gaseous composition, can grow to be much larger than terrestrial planets, which are limited by their denser, rocky makeup. With this understanding, we can now explore how planets form and how this process influences their size. Planets aren't born overnight. Their formation is a fascinating process that plays a crucial role in determining their size. Let's take a journey back in time, to the very beginnings of a planet's life, where it all starts with a protoplanetary disk. This disk is an accumulation of gas and dust particles orbiting a newly formed star. These particles, drawn together by gravity, start to clump, forming what we call planetesimals. These planetesimals are the building blocks of planets. As they collide and merge, they grow larger, eventually forming protoplanets. The size of the planet that forms depends on several factors. One of these is the mass of the protoplanetary disk. The more material available in the disk, the larger the potential planet. Another is the location within the disk. Planetesimals closer to the star are subject to higher temperatures, which can affect the type of materials that stick together. This is why we often find rocky planets closer to the star and gas giants further away. The speed of the planet's formation also plays a role. A faster formation process allows a planet to grab more gas from the protoplanetary disk before the star's radiation blows it away. This is how gas giants like Jupiter and Saturn come into existence. Then, there's the influence of other bodies in the system. Protoplanets can be thrown out of the system, or their growth can be stunted by larger neighbors. It's a cosmic game of survival of the fittest. So, when we talk about the birth of a planet, we're talking about a process that's influenced by a myriad of factors. From the mass of the initial protoplanetary disk, to the location, speed of formation, and the presence of other bodies. This formation process sets the stage for a planet's life. But gravity and atmospheric conditions also have a say in its size. Gravity, the invisible force that keeps us grounded, also has a profound effect on the size of a planet. Now let's dive into how this force molds the size and shape of celestial bodies. Imagine a planet as a colossal mass pulling everything towards its core. This pull is gravity, and it's what keeps our feet planted firmly on the ground. But it's not just about keeping things from floating off into space. Gravity also plays a pivotal role in the formation and size of a planet. A planet's size is inherently tied to its mass. The more mass a planet has, the stronger its gravitational pull. This increased gravity attracts more matter, allowing the planet to grow larger. However, there's a limit to this growth. As a planet accumulates more mass, its gravitational pull becomes so strong that it compresses the planet's matter, effectively limiting its physical size. Now, let's talk about the atmosphere's push. An atmosphere is a layer of gases surrounding a planet, held in place by gravity, but it's not always a peaceful coexistence. There's a cosmic tug-of-war happening, with gravity pulling inward and the atmosphere pushing outward. This push is known as atmospheric escape. It's when particles in a planet's atmosphere gain enough energy to overcome the planet's gravity and escape into space. This process can significantly impact a planet's size and composition over time. For instance, let's consider Mars, a planet once thought to have a thick atmosphere and flowing water. Over billions of years, Mars's weak gravity couldn't hold onto its atmosphere, causing much of it to escape into space. This atmospheric escape left Mars with a thin atmosphere, unable to support liquid water on its surface and significantly smaller than Earth. So, in the cosmic scale, a planet's size is a delicate balance between gravity's pull and the atmosphere's push. While these forces shape planets within our solar system, what about those outside it? Let's turn our gaze to exoplanets. Beyond our solar system lies a vast array of exotic planets, each with its own unique size and characteristics. This arena of far-flung celestial bodies, known as exoplanets, has broadened our understanding of the cosmos and challenged traditional notions of planet formation and size. Exoplanets are planets orbiting stars beyond our solar system. Since the first discovery in the early 90s, thousands of these fascinating celestial bodies have been found. They come in a dizzying array of sizes and compositions, from gas giants larger than Jupiter to rocky worlds smaller than Earth. Some of the most notable discoveries include the Kepler-22b, a planet about 2.5 times the size of Earth, located in the habitable zone of its star. There's also HD 209458b, a gas giant that's losing its atmosphere, creating a tail similar to a comet. Patterns and trends in exoplanet sizes reveal a universe of diversity. For instance, there's a surprising abundance of planets between 1 and 4 times the size of Earth, a category of exoplanet that doesn't exist in our solar system. However, it's not just the sheer variety that's fascinating. The size of these exoplanets can tell us a lot about their formation, composition, and even the possibility of life. For example, smaller rocky planets are more likely to be terrestrial like Earth, while larger ones tend to be gas giants. The discovery of these exoplanets has also led to the identification of new categories of planets, including super-Earths and mini-Neptunes. Super-Earths are rocky planets larger than Earth but smaller than Neptune, while mini-Neptunes are smaller than Neptune but larger than Earth and have thick gaseous atmospheres. These exoplanets challenge our understanding of what a planet can be, especially the intriguing categories of super-Earths and mini-Neptunes. They prompt us to ask, is there a limit to how large a planet can be? Or is the universe full of potential for all sizes of planets, each one as unique as the star it orbits? In the realm of exoplanets, super-Earths and mini-Neptunes are pushing the boundaries of what we know about planetary sizes. These celestial bodies intriguingly fall between the size of Earth and Neptune, a gap that's not filled in our home solar system. To start, let's delve into what exactly these planets are. Super-Earths, as the name suggests, are planets that are larger than Earth but smaller than Uranus and Neptune. They can be up to 10 times the mass of Earth, and interestingly, they seem to be the most common type of planet in our Milky Way galaxy. On the other hand, mini-Neptunes are slightly larger, with a size and mass just below that of Neptune. They possess a thick, gaseous atmosphere, much like our solar system's ice giants Uranus and Neptune. So what influences the size variations of these planets? A lot of it comes down to their composition and the conditions in their host star system. For example, the amount of solid material available in the protoplanetary disk during planetary formation plays a crucial role. More solid material can lead to a larger planet, while less of it results in a smaller one. Gravity also has a significant impact. A planet with stronger gravity can hold onto a thicker atmosphere, potentially pushing it into the mini-Neptune category. Conversely, a planet with weaker gravity may not be able to retain a thick atmosphere, keeping it in the super-Earth category. The distance from their host star also matters. A planet too close to its star could have its atmosphere stripped away by intense stellar radiation, reducing its size. On the flip side, a planet further away may be able to hold on to a thick atmosphere, allowing it to grow larger. As we continue to discover more about these exotic planets, we're also learning how the characteristics of a star and its solar system can influence planetary size. This exploration is not just about pushing the boundaries of our knowledge, but also about understanding the fascinating diversity of the cosmos. The size of a planet isn't just about the planet itself, but also about the star it orbits and the system it belongs to. Picture a cosmic dance where each participant, the star, the planets, and even the interstellar matter, contributes to the rhythm and pace. This dance, choreographed by the laws of physics, shapes the size and characteristics of each planet. The star at the center of a planetary system plays a pivotal role in determining the size of its planets. Stars emit radiation, creating a zone around them known as the stellar habitable zone. This is the area where conditions may be just right, not too hot, not too cold, for a planet to maintain liquid water on its surface, a crucial ingredient for life as we know it. It's also the region where terrestrial planets are most likely to be found. But the star's influence doesn't stop there. It also emits a stream of charged particles known as stellar winds. These winds can strip away a planet's atmosphere over time, especially if the planet is small and low in mass. In extreme cases, powerful stellar winds can even erode a planet down to its core, dramatically reducing its size. The characteristics of the star itself also matter. Larger, hotter stars emit more intense radiation and stellar winds, which can affect the size and composition of nearby planets. In contrast, smaller, cooler stars might allow for larger planets, especially gas giants, to form and persist. But let's not forget about the other planets in the system. Their gravitational forces can tug on a planet, affecting its orbit, rotation, and even its shape. This cosmic tug-of-war can sometimes lead to interesting outcomes, such as planets puffing up to larger sizes under certain conditions. As we consider these factors, we also need to ponder the relationship between a planet's size and its potential habitability. When it comes to hosting life, size matters, but it's not just about being bigger or smaller, It's about striking the right balance. As we delve deeper into the universe, we see that the size of a planet plays an integral role in its potential habitability. Imagine a planet too small, like Mars. Its weak gravitational pull struggles to hold on to a substantial atmosphere, making it a harsh environment for life as we know it. On the flip side, consider a planet too large, like Jupiter. Its powerful gravity draws in a dense, crushing atmosphere composed mainly of hydrogen and helium, conditions that are far from hospitable. But let's not forget about the middle ground where Earth comfortably sits. Its size and mass allow it to maintain a moderate atmosphere, rich in nitrogen and oxygen, along with a protective magnetic field, all of which are vital for supporting life. Yet, size is only part of the equation. The position of a planet in its solar system is equally critical. Enter the Goldilocks zone, a region around a star where conditions are just right, not too hot, not too cold, for liquid water to exist on a planet's surface. This zone is a sweet spot for life, as water is a key ingredient for life as we know it. However, the Goldilocks zone isn't a one-size-fits-all concept. It shifts depending on the star's size and temperature. For instance, red dwarf stars, smaller and cooler than our Sun, have a closer-in Goldilocks zone, while larger, hotter stars like Sirius have a more distant one. So, while we've found planets in the Goldilocks zone, their potential habitability is still a question mark. We need to consider various factors like atmospheric composition, planetary rotation, and magnetic field, to name a few. As we continue to explore the cosmos, we're faced with scientific challenges and exciting frontiers. The delicate balance between size and habitability is one of these frontiers, a puzzle that scientists around the globe are tirelessly working to solve. As we uncover more about our universe and its diverse planets, who knows what fascinating discoveries await us? As we push the boundaries of our knowledge, we're constantly faced with new challenges and opportunities in planetary science. Understanding the size limits of planets is no small feat. It requires us to grapple with complex concepts, like the interplay of gravity and atmospheric escape, the intricacies of planetary formation, and the influence of stellar systems. Yet these challenges are what make the field so exciting. They drive us to continually innovate, developing new technologies and methodologies to delve deeper into the cosmos. Take, for instance, the upcoming missions like the James Webb Space Telescope, set to launch soon. It's expected to revolutionize our understanding of exoplanets, potentially discovering even more extreme cases that push the limits of what we thought was possible. So while we have made strides in understanding the size constraints of planets, there's much more terrain to cover. As we continue to explore, we're constantly redefining what we know about the universe and its limits. Our journey through the cosmos has brought us face to face with the intriguing question of planetary size limits. We've delved into the criteria that define a planet, the role of mass and gravity, and the distinction between gas giants and terrestrial planets. We've explored the formation process of planets, the influence of gravity and atmospheric escape, and marveled at the diverse sizes of exoplanets. We've been introduced to super-Earths and mini-Neptunes, and considered the impact of stellar systems and habitability. The cosmos, with its infinite possibilities, continues to challenge and expand our understanding, reminding us that the universe is a vast and complex place. As we continue to explore, each discovery brings us one step closer to understanding the boundaries of the cosmos. Thank you for joining us on this cosmic journey. Don't forget to like, subscribe, and share your thoughts in the comments. Until next time, keep exploring the cosmos.